In the previous chapter, we were able to build a parser from a text string to a Haskell representation of our markup language, and we built an EDSL for easy writing of HTML code. However, our program is still not that useful to other users because we did not make this functionality accessible via some sort of user interface. In our program, we'd like to take the user input and then convert it to HTML. There are many ways to design this kind of interfaces. For example, get the text input via standard input and output HTML via the standard output. Receive two file names as a command line arguments, read the content of the first one and write the output to the second one. Ask for fancier command line arguments parsing and prefix the file names with flags indicating what they are. Or maybe some fancy graphical interface, or combination of all of the above. To make this interesting, we'll start with the following interface. If the user calls the program without arguments, we'll read from the standard input and write to the standard output. If the user calls the program with two arguments, the first one will be the input file name and the second one will be the output file name. If the output file already exists, we'll ask the user if they really want to override the file. On any other kind of input, we'll print a generic message explaining the proper usage. In a later chapter, we'll add a fancier command line interface using the library, and also read whole directories in addition to single files. But first, we need to learn about I/O in Haskell, what makes it special, and why it's different from other programming languages. Originally, Haskell was designed as an open standard functional programming language with non-strict semantics to serve as a unifying language for future research in functional language design. In GHC Haskell, we use a lazy evaluation strategy to implement non-strict semantics. We talked about laziness before. The requirement for non-strict semantics raises interesting challenges. How do we design a language that can do more than just evaluate expressions? How do we model interactions with the outside world? How do we do input-output? The challenge with doing input-output operations in a language with a lazy evaluation strategy is that as programs grow larger, the order of evaluation becomes less trivial to figure out. Consider this hypothetical code example, which won't actually type check in Haskell, and we'll see soon. This hypothetical program will read two integers from standard input, and then we'll subtract the second one plus 2 from the first one plus 1. Or so we would expect if this was a strict language. In a strict language, we expect the order of operations to happen from the top down, but in a lazy language, we don't evaluate an expression until it's needed, and so neither result 1 nor result 2 are actually evaluated until we wish to print the result of subtracting one from another. And when we try to evaluate minus, it evaluates the two arguments from left to right, so we first evaluate result 2. Evaluating result 2 with substitution means to replace occurrences of n with the input 2, and then evaluate the top level function plus, which is a primitive function. We then evaluate its arguments, which is read int from the std in, and then n. At this point, we are reading the first integer from the standard input. After calculating the results, we can move to evaluating result 1, which will read the second integer from the standard input. This is completely opposite of what we wanted. Issues like this make lazy evaluation hard to work with in the presence of side effects, when the evaluation of an expression can affect or be affected by the outside world. This includes reading, writing from mutable memory, or performing input-output operations. We call functions that have side effects such as add with input impure functions. And an unfortunate consequence of impure function is that they can return different results even when they take the same input. The presence of impure functions makes it harder for us to reason about lazy evaluation, and also messes up our ability to use equational reasoning to understand programs. Therefore, in Haskell, it was decided to only allow pure functions and expressions, ones that have no side effects. Pure functions will always return the same output given the same input, and evaluating pure expression is deterministic. But now, how can we do input-output operations? There are many possible solutions, and for Haskell it was decided to design an interface with an accompany type called I/O. I/O's interface will force a distinction from non-input-output expressions, and will also require that in order to combine multiple I/O operations, we'll have to specify the order of the operations. I/O is an opaque type, like our HTML type, in which we hide its internal representation from the user behind an interface. But in this case, I/O is a built-in type that is hidden by the Haskell language rather than a module. Similar to maybe, I/O has a payload type which represents the result of an I/O operation. When there isn't a meaningful result, we use the unit type, which has one volume, unit, to represent that. Here are a few I/O operations and functions that return I/O operation. Put string line takes a string and returns I/O of unit, get line returns I/O of string, get arguments returns I/O of list of strings, and so on. Notice that each function returns an I/O of something, but what does it mean? The meaning behind I/O of A is that it's a description of a program or subroutine that when executed will produce some value of type A and do some input-output effects during execution. Executing an I/O of A is different from evaluating it. Evaluating an I/O of A expression is pure. The evaluation will always reduce to the same description execution of the program. This helps us keep purity and equational reasoning. The Haskell runtime will execute the entry point to the program. The expression main that must have the type IO of unit in order for our IO operation to also run, it has to be combined into the main expression. Just like our HTML structure type, the IO interface provides combinators for composing small IO operations into bigger ones. The interface also ensures that the order of operation is well defined. Note that just like append we've defined for HTML structure, the combinators for IO are implemented as type class instances rather than specialized variants. For example, our append function in the beginning was a specialized version of append, tailored only for structure. This section introduces specialized type signature rather than generalized one because it's easier to digest, but we'll talk about the generalized versions a bit later. Our first combinator is pronounced bind, and it's the most useful of the bunch. This combinator takes two arguments. The first is an IO operation, and the second is a function that takes as input the result of the first IO operation and returns a new IO value, which is the final result. Let's look at a few examples using the function. First one is echo. We are reading a line from the standard input on the left of the bind. We receive the input to the right of the bind as an argument to the lambda function, and then write it to the standard output in the body of the lambda function. Bind's role here is to pass the result of the IO operation on the left to the function returning an IO operation to the right. Notice how bind sort of defines an order of operations from left to right. Here's the types of each sub-expression. GetLine is IO of string, putStringLine is a function from string to IO of unit, bind takes IO of string, function from string to IO of unit, and returns IO of unit. And the line is a string that gets thrown around. So the type of the whole expression is IO of unit. Also note that this example can be written in a more concise manner in point-free style. Second example is appending two inputs. This subroutine combines multiple operations together. It reads two lines from the standard input and prints a greeting. Note that using bind defines the order of operations from left to right. Because of the scoping rules in Haskell, honorific will be in scope in the body of the function for which it is its input, including the most inner function. Let's see a few more combinators. These two have the same type signature for IO and means the same thing. In fact, the first one is a slightly more generalized version of the second one and can always be used instead. The second one only exists to avoid breaking backwards compatibility. This operator for IO means run the first IO operation, discard the result, then run the second operation. And it can be implemented using bind. This combinator is useful when we want to run several IO operations, one after the other, that might not return anything meaningful, such as putStringLine or logs or whatever. Like with the previous two operations, Pure is a more general version of return. Pure also has the advantage of not having any resemblance to an unrelated keyword in other languages. Remember that we said IO of A is a description of a program that when executed will produce some value of type A and may do some input-output effects during the execution. With Pure, we can build an IO of A that does no effects and will produce a specific value of type A, the one that we supply to Pure. This function is useful when we want to do some uneffectful computations that depends on IO. For example, this confirm function that returns IO of boolean. If we try to return just true or false, it wouldn't work because of the type of bind. The right side of bind in our code example must be of type string to IO of boolean. This is because first, getLine is IO of string, so the type A in the type signature of bind should be the same as string in the instance, and confirm is IO of boolean, so B should be a boolean. Another way of looking at this is the case expressions should have matching types. The last one is an IO, it means that the previous two should be an IO as well. These two are the same. The first one is a fmap function and the second one is an infix operator version of the first one. Use it at your own discretion. What if we want a function that reads a line from standard input and returns it with an exclamation point at the end? We can use a combination of bind and pure. This pattern is unified to the fmap function. Fmap applies a function to the value to be returned from the IO operation, also known as mapping over it. By the way, have you noticed the similarities between fmap and map? Here's a list of IO combinations we ran into. First one is bind. It's chaining IO operation, passing the result of the left IO operation as an argument to the function on the right. Second one sequences two IO operations, discarding the payload of the first one. Third one lifts a value into IO context and does not do any IO effect. And the last one applies a function or maps over the payload value of an IO operation. The beauty of IO is that it's completely first-class construct in the language and is not really different from maybe, either, or structure. We can pass it to the function, put it in the container, etc. Remember that it represents a description of a program, and without combining it into main in some way, it won't actually do anything. It's just a value. Here's an example of a function that takes IO as an input. It takes IO of boolean which returns a condition and an action. Based on the result of this condition, it either executes this action or not. And this is how it can be used. Notice that putting string line IO is awesome is not executed right away, but only if it's when IO returns. And they're all combined into one main expression. What we see here and before has great consequences to the Haskell language. In our HTML type, we had a function render from HTML to string that could turn an HTML to a string value. In Haskell, there is no way to implement a function such as execute that goes from IO of A to A. That preserves unity and equational reasoning. Also, IO is opaque. It does not let us examine it. So we are really bound to what the Haskell API for IO allows us to do. This means that we need to think about using IO differently. In Haskell, once we get into IO, there is no getting out. The only thing we can do is to build bigger IO computations by combining it with more IO computations. We're also not allowed to use IO of A in place of an A. For example, we cannot just write getLine plus exclamation point because the concatenation expects both sides to be strings, but getLine type is IO of string. The type do not match. We have to use fmap and return type must be IO of string, like we've seen before. In Haskell, we like to keep IO usage minimal, and we like to push it to the edge of the program. This pattern is often called functional core imperative shell. In our block generator program, we want to read a file, parse it, convert it to HTML, and then print the result to the console. In many programming languages, we might interleave reading from the file with parsing and writing to the file with the HTML conversion. But we don't mix this here. Parsing operates on the string value rather than some file handle, and HTML is being converted to a string rather than being written to the screen directly. This approach of separating IO and pushing it to the edge of the program gives us a lot of flexibility. These functions without IO are easier to test and examine because they are guaranteed to have deterministic evaluation, and they are more modular and can work in many contexts. This pattern is often a good approach for building Haskell programs, especially batch programs. We'd like to start building a block generator, and we want to have the following interface. If the user calls a program without arguments, we will read from the standard input and write to the standard output. If the user calls the program with two arguments, the first one will be the input file name and the second one will be the output file name. If the output file already exists, we'll ask the user if they want to override this file. On any other kind of input, we'll print a generic message explaining the proper usage. We're going to need a few functions. Get the program arguments, read all the content from standard input, read all of the content from a file, write a string into a file, and check whether a file exists. First, we have to implement a function process, which will parse a document to a markup, convert it to HTML, and then render the HTML to a string. And then we want to implement the imperative shell for our block generator program. We start with main, pattern match on the result of getArgs, and decide what to do. As the chapter suggests, we only need to glue things together. First, we parse a document to a markup, then we convert it to HTML using the function above, and then render the HTML to a string. The function we just wrote can be moved to main, along with the two functions we saw in the chapter, when.io and confirm. Another part of preparation is import. We have to import the does file exists and getArgs function, but we don't have to import getContext, read file, and write files because Prelude already imports these functions for us. Last import is convert and qualify the other imports. First step is to get arguments. There are three possible options. First one, there are no program arguments, there are two arguments, and everything else. The easiest one is any other kind of program arguments. It means the user passed 1, 3, or more arguments. We have to tell them how to use our program. We can print a help message. For now, we can tell the user to run GHC, our main file, and optionally pass input file and output file. If there were no program arguments, we are reading from standard input and writing to standard output. We can read the standard input with getContents, and then we can process it. Because we don't have a title, we can pass no title or empty title and the content. And then we can write it back to standard output with putStringLine. And the last case, when the user passed input and output file paths as program argument. First step, read input file. Then we have to check if the output file exists. If the file already exists, we have to ask for confirmation. Otherwise, if the file does not exist, we write to file without any confirmation. We have some duplication here, and because IO values are just values, we can extract them into a variable. While using bind to chain IO actions is manageable, Haskell provides an even more convenient syntax sugar called do notation, which emulates imperative programming. A do block starts with the do keyword and continues with one or more statements, which can be one of the following. An expression of type IO unit, such as putStringLine, or if true then putStringLine yes, else putStringLine no. A let block, such as let x equals 1, or multiple let declarations, such as let x equals 1 or y equals 2. Note that we don't have to use the in keyword in this case. And so we can do bindings from variable to expression such as line and getLine. And the last statement must be an expression of type IO something. This will be the result type of the do block. These constructs are desugared or translated by the Haskell compiler to regular expressions, Larians, and other functions that we saw before. For example, the first greeting function is a just synthetic sugar for the second one. It's important to note the difference between let and bind. Let is used to give a new name to an expression which will be in scope for subsequent lines. And bind is used to bind the result A in IO A action to a new name, which will be in scope for subsequent lines. For example, when we have a code let greeting equals hello, we use equals operator. We have string on the left and string on the right. Both sides are interchangeable. When we have a code let my getLine equals getLine, we still use operator equals, but type of the left side is IO string and the right side IO string as well. We just created a new name for getLine. But in case we have name bind getLine, we use bind operator. So the type of the left side is a string, while type of the right side is IO string. Technically, this bind arrow is not an operator. It's a synthetic sugar for actual bind plus lambda, where we bind the result of the computation to a variable. Do notation is very common and is often preferable to using bind operations directly. Let's translate the glue code we've done for the block generator to the do notation. We can switch to do notation in case of no program arguments, as well as in case of input and output files. We bind the content, we bind the exists variable, we keep the let as it was, but we can drop the in, and last thing, fix the arguments. Then we can use it in when IO function. We can also modify the confirm function to use do block on the outside and on the inside, in case of invalid response. In this chapter, we discuss what purely functional means, where the initial motivations for being purely functional comes from, and how Haskell input-output interface allows us to create description of programs without breaking purity. We also achieved a major milestone. With this chapter, we have implemented enough pieces to finally run our program on a single document and get an HTML rendered result. However, our command line interface is still subpar. We want to render a block with multiple articles, create an index page, and more. We still have more to do to be able to call our program a block generator. So let's keep going.